So hello everyone. Today's LeetCode is going to be serialize and deserialize binary tree. So serialization is the process of converting a data structure or object into a sequence of bits that can be stored into a file or memory or transmitted across a network connection link to be reconstructed later in the same or computer environment. Okay, so basically serialization is the process of changing a data structure to be easier to store. And in our case, the serialization is going to be changing the data structure, which is a tree, into a string. So design an algorithm to serialize and deserialize a binary tree. So this is the initial data structure, and there's no restriction on how you serialize/deserialize the algorithm should work. You just need to ensure that a binary tree can be serialized to a string, and this string can be deserialized into the original tree structure. All right. So basically, we are given this tree, right? So it is a bunch of nodes, and then we need to serialize it into a string form, and then from that string form deserialize it back into a tree. So we have two functions that we need to make, right? And their process is going to be they take the so they serialize the tree first, and then they give it back to be deserialized, and that way they can see if the original tree that they've given is the same one that we are returning. So this function right here is necessarily returning a string, and this one is necessarily returning a tree, right? Or just a node, the root node, basically. Does it make sense? Is it cool so far?
Yeah.
All right, great. So basically, if we have this this tree right here, then it's gonna be given us starting with the first node or the root node, which is 1, and then we need to serialize it into some sort of string. Now they're not really strict on what the string should be like or how it looks like. They gave us an example with how they usually do their strings, right? This is the one that they usually do in like as examples, right? And so they are not really giving us any like you necessarily have to follow anything, right? They said just like be creative. Dennis, can you please mute your mic? I can hear some background noise. All right. So I'm gonna mute you, Dennis. Sorry. So, all right. Now, they said that we do not necessarily need to follow their own format, but to just be creative and come up with different approaches. Now, there are two ways of doing this, of either like doing BFS or DFS, obviously. So we need to, I guess, decide on which way we want to go, and that will decide on how our tree is going to look like in serialized form. And we know there are different types of traversals, right? There is the pre-order, in order, we have the line traversals. I feel like we need to go in that direction, or we can come up with our own type of, I guess, serialization that would basically help us in the deserialization to make it easier. So does anybody have any questions? If not, any ideas on how we can start this?
Yeah, I have a question.
All right.
Can you elaborate on the last point you mentioned that we have different approaches because uh, maybe I misunderstood, but I see in front of me that is it's using in order breadth first traversals. So because as I see in the output 1, 2, 3, 4, 5. So ain't that pointing at only one solution, or I misunderstood something?
Okay.
I
So
mean, just breadth first, obviously.
this is their way of visualizing the tree into like a written format like this. But this is an actual tree, right? So the input is the actual tree, the root of the tree, right? This is just their way of making it into a string, or in this case, like an array. And also, the output is also going to be a tree, or the first or the root node of that tree. This is just their way of visualizing it into. So this is how LeetCode serializes binary trees. Um,
So
basically,
it's up to us to.
so it's up to us to make our own like format or like algorithm to make this
w-
tree into a string and then back to a tree. The input
which
and
may be in a
output,
different sequence.
no, in the same sequence, is in the same like order. So
Okay, so maybe I just have one way of solving it, and I don't know somebody else. That's why I'm confused.
perhaps,
So yeah,
okay, yeah. But the
got you.
output is not going to be like this. The output is actually going to be like a node object, one of these objects, like a tree node object.
Uh-huh.
Okay? So both the input
Got
and the output are going to be trees. But between them, they're going to basically run both of these functions. This one is going to make it from a tree to a string, and this is going to take it back from a string back to a tree.
uh,
All right? Is that clear?
thank you. Yes.
Okay, any more questions?
Um, I think that this problem consists of two parts, right?
Can you repeat, please?
Like uh, deserialization and serialization. Like serialization is a part, and deserialization is a whole another part. Like
Yes.
I think I saw problems on deserialization. Like you are given the traversal of the tree, and then you should construct the tree from the traversals, right? Like I don't know.
Well,
Uh,
technically, yes, but it is based on whatever you decide, right? So your
yeah.
string output should be whatever helps you make the serialization easier, basically. So it doesn't
Okay.
necessarily need to be one way of traversal, but
Yeah.
whatever
Yeah.
you decide, basically. Right, so any ideas on how we can start this?
Um.
I believe in BFF,
I
BFT, like breadth first traversal. If this is a normal binary tree, so we move, do breadth first traversal, and we just wherever we land, we just save it in like a queue. Just literally breadth first traversal. Whenever we go to a node, we added it. If we face like a if but rather than if we want to print the ID, the values inside the node, that when if we're doing this, we skip actually nulls. No, we just here we will make the traversal, but if we face a null, we will actually add it to the list. But of course, not adding it to the queue as the next uh, step.
So you're
I think
suggesting we use a BFS. Go on. Go on.
I think yeah, level order traversal would be good because it will make the deserialization process easier. Maybe.
Awesome. All right, let's start with this. So basically, what is it called? Level something reversal?
Hmm?
What is it called? Where you go to the
Level
side?
order.
Level
Level order.
order. Okay, okay.
Yeah.
So, traversal. What do you call that? Traversal. Level
Sorry,
order
I'm
traversal.
sorry. What does BFS stands for?
Breadth
Breadth,
first
breadth
search.
first search.
Search. Okay.
So
I think they are
basically,
the same, right? Breadth first search in trees level order traversal, right?
Yeah, I think they are the same. Yeah.
yeah,
Yeah.
in the depth level, same level. Okay. So
Yeah. Yeah.
basically, we just go in this order. So one, two, three, four, five, right? instead of, for example, pre-order traversal would be 1, 2, and then 3, and then 4, and then 5, but I guess they're the same in this case. But if we had, let's see another example from there. Let's check this one. So for example, this one in pre-order traversal, let's take this image back to Slowly Draw. So basically in this case, if we have level order traversal, it would be 5, and then 4, 7, and then 3, 2, and then minus 1, 9. And these in this order. So each level, we go through all of it, and then we go to the next level. In the pre-order traversal, it would be 5, 4, 3, minus 1, and then we go back to 7, 2, and 9, right? But we also need to keep track of the nulls, right? So we have a null here, another one here, and here, and then here and here, right? So we need to keep track of this. So we said that using BFS, we're gonna go into level order traversal. So in this case, it's gonna be 1, 2, 3, 4, 4, and 5, right? So I guess usually with BFS we use queues. So I guess we can do that. We can, as you said, we can go through the tree level by level. So 1, and then we add 1 to the queue, and 1 adds its children. So 1 adds 2 and 3. And now in the next iteration, 2 is going to be popped. 2 is going to add its children. In this case, it's null and null. And we need to have a way to put things in place of null. So in the example of LeetCode, they used null, right? We can just use like a dot or a hashtag or anything to make it known that this is a null child, right? So for example, 4 has 2 children, but one of them is 3, is a node, and the other is just a null. So in here we have a, I guess, a queue, right? This queue is going to hold the root of the tree, right? And now once 1, as I said, then it pops 1, it explores its children. The children are 2 and 3. Once it goes to 2, the children are null and null. So these need to be saved, right? So we put either a dot, a hashtag, whatever, to I guess, to symbolize that we have null children. And if we have null children, if we don't, then we just put the actual number of the node, and then we move forward. We have 3. So let's visualize that. And let's say this is our queue, right? And let's say it starts with 1, right? Now when 1 is popped, it's gonna add 2, and it's gonna add 3, right? And then 2 is popped. So once 2 is popped, it's gonna add nothing to the queue, but it's gonna symbolize that it has 2 null children. And then it moves on to 3. 3 has 2 valid node children, so it's gonna add 4. Once after it's popped, it's gonna add 4, and then it's gonna add 5. Now 4 is also null, so it adds null children. 5 is null, it's gonna add null children. If we show it as like a string, so our string is gonna start with 1, and then it's gonna go to 2, and 2 has 2 null children, so it's gonna put 2 empty children. Moves on to 3, and 3 has like 4 and 5, so it's empty. So it's not empty, so it's 4, and then 5, and 4 has 0, and then 5 has 0. Does it make sense?
Yeah, it does.
Yes. Okay. Now can we write down a little pseudocode for it? I guess we can just do
Well, I have something. I don't know if it's correct or if it be done or not, but
okay.
which is just thinking maybe before we lose focus, we quickly think of how we might deserialize and then go back here to code actually serializing. We
Okay.
think this is
All
good.
right. Sure, sure, of course. Then let's
I,
think of how we can deserialize this.
yes,
Why there are two dots after the two?
Because
Should
2
should
doesn't have any children.
Yeah, but if we did a level order traversal, should the one have? I think the one should be followed by two and three, and then two dots, right?
All right. I guess, yeah, yeah. So let's see what they add. So in theirs, yeah, you're absolutely right. So theirs, I believe, is in order in is level order traversal is 1, 2, 3, and then null null, and then 4, 5. You're absolutely right.
Yeah.
Okay. So how we did this earlier is you have 1, and 1 adds 2 and 3. Now 2 doesn't have anything, so it doesn't add anything, and it goes back to 3, and then 3 adds 4 and 5, and then 4 and 5 has 0 and then 0. Okay, we'll get back to this. We'll get back to it. Now in the deserialization, um, let's see how we can. So in deserialization, we need to go from this to this, basically. So the first element is the root, obviously. These elements, so 2 and 3, are as children. And from here onward is the children of 2 and 3, right? So the first children are the nulls, and the next children's are 4 or 5, and after them again is the emptiness, is the true null elements. So any ideas on how we can go from this string back to this? And keep in mind that some of the numbers can be negative. But yeah, the value can be from -1,000 to +1,000. So any
just a
ideas?
second.
I
Let me
think I
think.
think there's a formula for the left child and the right child. So if we start from the left, which is the root node, which is here 1, so the left child for 1 is 2. The in order to get the index for the 2, I just need to multiply 2 by the index of the root node, which is 0. 2 times 0 plus 1. So 2 times 0 is 0 plus 1. Now the index of the left child is 1. And for the 3, I just need to do the same equation, but I need to add instead of 1, I need to add 2. So 2 times 2 times the index of the root node, which is 0, plus 2, which is 2. So if we reverse this, we can get from right to left.
Okay. So from right to left, you want to go from this side back to the root, right?
Uh, Not exact. Yes, yes, yeah.
Technically start
So
from 1 and then link in each new node to it, right? I believe this is the BFS way. Going from right to left, I believe, should be like a recursion type thing.
um, I didn't get what you are trying to say
So
actually.
you
Why
want
the
to start from the
recursive
leaves
solves?
back to the root, right?
No, no, I don't want this, but this is was your very first question. You said that if we wanted to get from right to left,
Yes.
very early in your speaking, you said that
Yeah,
we
yeah,
need,
because I asked you
yeah.
because
So
I
so this
remember
is
you
why,
said that going from right to left. So
yeah. So this is why from right to left, I just need to I need to reverse this equation. So instead of multiplying by 2, I need to divide by 2. And so let's say we have a data set of three elements. So let's say we just have 1, 2, 3. This is our tree.
Okay.
And I wanted to go from I needed to know the parent of the node 3. So I right now my cursor is at node 3, and I needed to know I need to know the parent of this node.
All right.
So 3 is at index of length of data minus 1. So which
It's two
is
in this case.
yeah. So I think
But
2
two divided
divided
by
by
two.
2 minus 1. I think this is the parent, yes. And I need to take the absolute value as well when it comes to calculating the parent.
Divided by
And
index.
and also for
I
the
think you're trying to say that we should treat the string as a heap data structure, something like that. Like if we start from the first element, we 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 know that the next two elements are the children of the first element, and the fourth and fifth element are the children of the second element, and so on, right?
Good idea. So basically, let me just keep this one. I go back. Okay. So you said that we start from the first element, right? And we know that the next two numbers are its children. And the next two numbers are the children of the first one. The next two are the children of the second one. And you keep going, right?
Yeah, yeah,
Exactly.
Okay, that is a good idea. So
yeah.
basically we could add like a cube, right? And the first element would add this one and this one to the cube as their children and make nodes for them, right? And then once you go to the second element, is gonna skip to this, so the
Uh,
index.
I think we can solve it without using queues, maybe because of the above formula: 2 index plus 1 and 2 index plus, I think,
Plus
2
two.
index plus 1 and 2 index plus 2, right?
Yeah.
For the second element. So for the first element, I don't know. Like we can use just a regular loop to through the string, maybe.
And
Like if
so
we
let's
start by
let's let's go through it. So let's go here. So you would go through one, and one would
yeah,
give you, so you said two
two,
divided by the index. So in this case,
yeah,
the
I would
index
say like
is,
the left child left would be 2, the element at index 2, 2 times the current index plus 1, and the left child would
so
be the element.
the current index is 0, right? So is it 0 divided by 2?
No, 0 times 2 plus 1.
Oh, so it's this. Okay. All right, right. So basically 2 times 0 plus 1. In this case, it's 1. All right. Now this is left. The
I
right would
yes,
be
2 times 0 plus 2.
plus 2.
This is the right child. Now
And
we
the
know that we traversed like 3 element. We should go to the third element directly. Like the next index would be uh,
next
2i plus
index
3 or something like this. Like
wouldn't the next
or
element be actually 2, since this is the root of whatever next we are attempting?
yeah, yeah.
Okay, so at 2
2 times 1 plus 1.
times 1 plus 1, and in this case it is 4. 0, 1, 2, 3.
Yeah. And the stop criteria will be the length of the array. Like if we reach a number out of the array bounds, we should stop adding elements, and this means that the tree is already constructed right now, right?
Okay. All right. So we keep looping through these elements. So 1, 2, 3. And if it's a 0, we can just skip it. And then 4. And we can almost guarantee that we're not going out of bound. So for example, 0, 1, 2, 3, 4, 5. Then 5 times 2 is 10. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it is going out of bound.
Um, if we reach or if we go out of bound, this means that the tree is already constructed, right? Like let's say for the element 2, the current indexes would be 2 times 1 plus 1, which is 3, right?
Is this formula like linked to a specific traversal order?
Uh, this formula is to reconstruct the tree from the from the string.
Yes, but to
Like
which to which
if we treated the
which
string
order
as a heap.
traversal? I understand you,
But
but it
yeah,
is gonna have different order for each order traversal. It may like be working for another um traversal way because I feel like it's not gonna work for this since
Sorry,
like it's
Sam.
going out of bounds.
No.
and why is that?
Okay, let me Google it. Because I feel like since it is going out of bounds, for example, in this 4,
when
right?
when the when the formula goes out of bound, this means that the tree is already constructed. Like
Right.
let's start with the 2. Can we complete with the example? Let's start
Okay,
with the
so the
2
two works, but I feel like the 4 doesn't.
because 4 is already the last element.
All right.
If we
Okay. All right.
I got
So
you, but 4 has
so basically we check if our index is bigger than the limit of the string, then we don't do
add an
anything,
element.
right?
Yeah,
Okay, great. So for E, and so I guess we just sort of code. So we loop through our string
yeah,
and we do this formula. So we go left first. So we do left equals index 2 times index plus 1. And then if, I guess, string left, so if left is smaller than the length of the string,
yeah,
and the string left doesn't equal like our null parameter, then we make a new node, and then what then? We link it to what? This is the left of something. So we should first make,
we should start with the first element in the, like if the, let's say that we have a head of, or like a root. Let's say that there is a
so
root.
we make a node for the root, right?
Yeah, we
And
start from the root, and
and
then
now we link
if
this
the
node
root
to
is
the
null,
root.
this is the
Oh,
first number in the string would be our root. Then we add elements to this root. Like
right.
in this case, left would be 2, right?
Okay.
The element 2. So root dot left
And then we do the
Yeah.
same thing for the right.
Yeah.
And then what else? How do we go to the second one? So I believe this should be inside. But no, no, it doesn't. It doesn't. Since we already have the nodes, we just don't have them on hand. Do you get what I mean?
No.
So
I didn't get.
basically, we have the root, right? So the first iteration of us having one, and we link two to one and then three to one. But the second iteration, where we have two, the node of two is already created. So do we recreate it? And we don't have it. So far, we only have this root. And here it is created, but it's not saved somewhere. The
Yeah.
queue allows
I have
us to make this node and add it to the queue so we have it on hand for the next iteration.
I see a pattern, but I see a pattern, but I didn't really yet come up with a solution. I see that
Okay.
you know one notice that when we're making breadth first, we're we're reading actually an existing tree. We're reading the children of the nodes. Like I'm sorry, reading the nodes and adding the children of the nodes because they already exist. We adding them to the queue. So
Yes.
that's note. Second note. I'm jumping. I know. Second note. If you look at this list here of strings, every node, the children of it is two indexes afterwards. Like one will have. I'm sorry. Two, yeah, two indexes, and like one is two and three, and two you will skip two. Like except from the first one, except from the first one, your children will be two index and there's will be like two indexes gap from you. So one, okay, we have two and three, but for two, you will skip two, and it will have like, oh god, I did I screw it up?
I
My
believe
bad.
you're
I
going in the
I
right
believe
direction.
I was
I believe that
I,
it doesn't necessarily uh, two indexes, but yeah, I think there is a pattern. Like it's the same as the idea of the level order traversal. Like whenever you pop a node, two nodes will be added to the end.
If they are
So
valid.
I think uh, to
Um,
make it
Hey,
clear for
Sabah.
you, why we can make the above tree of 1, 2, 3, 4, 5 like a complete tree. If the tree was a complete tree, I think it may not be two indexes exactly, but yeah, there is a pattern.
well
Yeah.
the thing I thought about is that we create like we create nodes and add them to the tree. We just I think I confused myself looking at the pattern. You know, 1, 2, 3 dot dot 4, 5 4 dots. I saw a pattern, but I forgot it for a second. So if you take a look at the pattern again and see what children are like are the which the father of which index, what's the distance between the father and the children, we can instead of do breadth first, but instead of adding an existing node, we just create it and add it to the code to the queue and move on like we were actually serializing, not deserialized. Again, I'm not putting my finger onto the hard code solution, but you see the pattern I'm pointing at.
I'm seeing the pattern. I'm also getting a little bit confused. So, so you said we're using a queue, and then you make the node, you attach the node, and then you add it to the queue.
Yeah, and make breadth first, like you know we're creating a node because we see this list here 1, 2, 3, 0, 0 dot dot 4, 5. Whenever we're in a node, we see which of these numbers are actually its children. We add it to them, so we create nodes. We attach it to the node that we are in, then add it to the queue and continue traversing. You got it?
All right. So
You're
basically,
creating. It's kind of like you're creating a tree while traversing it.
Yeah,
Make a
that's
little
exactly. Okay, well, I
good.
guess not the nodes, but the queue.
Good, it makes sense. So
So make the new node, attach the new node, add the new node to queue, right?
I
And
think
then
so.
do the same here.
Okay.
Copy.
One, two. Actually, I don't know.
So here it's not gonna be root, but just I guess it's root in this case. Does this look okay?
Yeah,
Okay, and then at the end, what are we returning? So since we are looping through the queue, we need to find a way to keep track of the index, since we're
Yes.
not technically looping through the string, but rather the queue. Can we just have like a
Okay.
variable here called index that we just keep like incrementing as we go?
Hang on. Okay, so if oh, hang on. Okay,
Yeah, it makes more sense.
All right. So now that we have index 0, so 2 times 0 plus 1, and then it will give us left, and then it will give us right, and then we increment it. I feel like it's going to be a bit weird once we get here, right? Since it's going to be, the index is going to be 3, but we are going to be at 5. So I believe if we find like so we're just,
Um,
this
I'm
is
still
a
confused
lot. So, okay, okay.
why you needed to add the node to the queue
Okay, okay. So
for both the
think
left
of
and the
this, think
right.
of this. I have a loop. I have a loop, right? I at first have only the root, which is an object, right? A node object. Once I attach 2, right? Which is also a node object. And I attach 3, which is also a node object. Once I want to go to 4, I still only have 1 at hand. I don't know where to attach 4. Where am I saving these 2 to attach the children to?
I there's someone opening his mic and it has
I
a
thought
noise
it was one
background.
of you. Okay. Um,
So like I didn't get to hear you clearly, sorry.
okay. All right. So basically, I have 1, which is the root, right? And then I have 2, which is also an object, a node object that I'm attaching to 1. And I have 3, which is also a node object attached to 1. But so far, I only have root, this object, which is 1. Now, when I move to 3, where am I saving 2 and 3 to attach 4 to? This 3, I don't have it on hand. I created it, I attached it to 1, but I don't have it. So, for example, here I created 2, right? Root left, and I created the node, and then root right, and I created the node. But I still only have root in a variable. I only have this,
I got
and
it, got it.
root kids are like 2 and 3. 4, I don't know where to attach it to. If I add it to a queue, then I can almost like save it and then go back to it. I will have it on hand once I pop the queue. Does it make sense?
Got it.
Okay, great. So now we just return root. So I was now wondering how the index situation is gonna be when we get to these null elements, because we increment it at the end of each run, right? So for example, e plus equal 1. The issue would be if I go to 1, I go to 2, and I go to 3, and 3 is gonna add 4 to the queue. So we are skipping these two. How are we
Uh-huh.
like dealing with this? Because the next index should be 5, but it's gonna be 3. How are we dealing with these two in the middle that we are skipping?
I think we
No
I think you
point.
could like,
should look through the whole string.
So we
yeah, you
go
could
through
like
the
look
whole
through
string.
your string
Huh?
and then the memo. Sorry, can I go ahead? I think like you could look through the whole string and the computer memory is just going to add some random number there for you.
Okay, so if we're
So
going
it's
through this,
valid.
so we're going through
So
1
if you jump,
and 2 and 3, and I got here, and the next element is 4 in the queue, but the next element is where I am currently is the first null. What do I do? Am I
If
still popping the queue? Should we add like an extra if guard here?
yeah,
So we can
yeah, and
say
then continue. You right.
if the current element equals point, then we just continue, right? Else, then we just do this. That makes sense.
Yes.
But we also need to guard against the queue being empty. But I guess I don't
Will the
see,
queue in the empty?
because at the end here the queue is gonna be empty, but that just means that we don't have any more elements to add, which I guess is okay. I think we can write that, but we still have not really discussed the first part. This is the deserialization. We can, I guess, test it and then go back to serialize. We can like return and like hard-coded string and test the deserialization and then go back to making the serialization. Just so we know this is like working 100%. What do you think?
I agree.
Okay. So we first let's decide on the string itself. So we said this is gonna be the string. We have nodes and then we have these that mean null, right? But we also can have negative numbers. If we were to loop through the string, then this negative is gonna be in the way. What do you suggest we do?
Well, well, that's gonna affect the index of our
Yeah, not only is it
string.
gonna affect, but it needs to almost be linked to this. Like -2 should be one element, not minus alone and 2 alone.
Okay,
So
so I've
but
got a small quick idea that I think since the string that we will create will not affect nothing, it will directly talk to the deserialization because
Yes.
the output that the checker needs is just a tree. So we can double the string. Like the just think of the if you distract yourself with this, I think it will damage the logic. But think we can double the string, so each character is actually each number or each whatever is actually taken what do we call it? Two like two spaces. So we have like instead of one minus two three, we have positive one minus two positive three, and the index we just double the index by two. Got it?
You might be overcomplicating it just a teeny tiny bit. Um, since
Okay, so
we're
we
why
need
you
checker. It could be tiny complicated, but it could save us a bunch of if statements that okay if this number
there
is
is an
actually
easier
two
way, though. There is a,
network
but go
again.
on. Somebody else wanted to talk. Go on.
Oh yeah.
why you using a string? What if we use like integer array? Or
So,
did it provide a string sometimes?
so serialization is required to return a string. right? So this function is receiving a string. We can do whatever we want to that string, including just splitting that string into integers.
So let me see the input.
Hmm?
Okay, I can see it from here. Don't worry, I can see it from here.
I did not hear that.
I'm asking if I could see the input, but I can check it from here. Let me check it.
The voice keeps breaking a little bit. Can you please
Asking
repeat?
if I could see the input, but I can check it from here.
Can you can check the input? I mean, it is
To
a
the
string.
question.
The question, the string will be deserialized. I'm honestly, I don't understand what you're trying to say. I'm sorry. Okay. So basically, this function is receiving a root object and returning a string, and this function is receiving a string and returning a tree node. So the string that we're getting from the data, we can technically modify it in any way we want. And we can also modify the string that is going to be returned from this, right? So instead of leaving this just as a like a string like this, we can split it into independent element, right? And with that opens the opportunity to maybe add the limiters between each element, which we can split by, and basically it will give us this number as one element instead of this as a connected string. So for example, if our serialization function returned a string like this, for example, where we add just like a comma in between each element, then when we come to deserialize it, we can split this string by these commas, right? And that will give us an array of strings of 1, -2, 3, 4. So we don't worry about the negatives. Does it make sense?
Yeah, yeah. I think makes sense
Okay.
to use commas.
All right, great. So now if we assume that our input string is like this, or any, technically anything would count, so we just do a bit of this. So that will make our string an array, right? And now this array, we can loop through elements of the array, which is 1, -2, and we can like turn this, since it's going to be like a string rather than just like a number, we can just convert it. But I've noticed that they don't care if the value of the node is in string or integer, so you can just skip that. But for now, we have these elements. So we first of all need to split our string. So we have a string data. We can name them like nodes equal data dot split, right? And we specify by which delimiter we're splitting. So we have a comma, right? Now we make a node for the start, or the root node, right? So root equals this tree node object, and it's gonna have the the value of the first element, right? Since it is in here, it is always the root element of the whole tree. So we can do nodes 0. All right, so now we made the node for the root. We now loop through the string, so for index in range len nodes. That way we give the
Can I,
indexes.
hello?
Yes?
Yeah, can I mention that you're going to have an error on line 25 because when you split the string, the values are going to be strings, right?
Yes.
And your tree node object is going to expect a value that's an integer.
Okay, I just said earlier that as I was like playing with this earlier, it didn't really matter what type was the actual values. I can make it ints now, and we can check later if that's actually true or not. But I forgot to do it later on, and it didn't give me any error, so I don't think so,
Oh, okay,
but
fair enough, fair enough.
we'll do it for now. Okay, so for range and index, blah blah blah, if the current element, aka nodes 0 or nodes index equals dot, then we continue. Else, now we need a queue. So our queue equals dq, and it should have the main element, so the root, right? So it's gonna have our root. Now we pop the queue, so q dot, I guess node equal q dot pop left, right? And then now left equals this, and right should also +2. So left is 2 times index plus 1, and then now if len is smaller than len of nodes, but yeah, so if len is smaller than len of nodes and nodes left doesn't equal dot, then we make a new node. So let's give it L. So L is the same as this. Instead of 0 is going to be left. And then root, or in this case it's our node, node.left equals L. And we add the new node to Q. So u dot append L. And do the same thing for R. So R 2 times +2. And if right is smaller than nodes and nodes right doesn't equal dot, then let's just copy this. R right equals R, and then we append R. Alright, and then we return root. We need probably some guard against like popping, but I guess we already did that. So let's return like a hard-coded string here. Let's give it, for example, like this without the brackets. And let's see if this one gives us something. So we need to, I believe, let's remove this minus. Okay, so this one is the same tree, and we can see that it reconstitutes the tree correctly, right? So this one is correct. This one is only because we hard-coded the string. All right, so I believe our deserialization worked. I'm worried about this 0 for elements that are empty. So in this case, this is gonna return an empty string. So if our tree was null, this is gonna give us an error since 0 does not, since it's basically empty. Not only that, but also I believe the split messed that up. So we could add like a additional if guard here that would tell us like if the element is empty or there is something in it. So I'm not sure how we're doing the serialization for an empty element. So if it's returning like an empty string, but we can add like something here if data equals something, right? Until we know what an empty string or an empty tree returns here, then we can put it in this spot. Then we just return none, aka just an empty tree or no tree at all. All right, now we can move on to the serialization, which is basically just turning this tree into level order traversal. So, any ideas? Any ideas?
For the serialization, you mean?
Yes.
We can initialize our queue, then we append the root,
Mm-hmm.
then we just pop left and then append whenever the node it has a left or right child
So we add root
inside
to
a,
queue.
a while loop. Yeah, so first things first, I need to add the root. Then inside a while loop, my termination condition would be while the queue is not empty. I need to pop from the root. I need to pop from the beginning. Then the pop node, I need to check if it has a left child or right child,
Okay.
and I need to append accordingly. And
So
I
if
keep doing this
left,
while the queue is not empty.
okay. So if left, then append left. And then we need to add it to some sort of string.
I think either we need to append the whole node or just the value.
Okay. So we append left. So I believe we're appending just the value since it is a string.
Yeah, so yeah.
Well, we're appending the node itself, but we're adding the element to the string, but with just the value. So add to string or add value to string, right? And we do the same with right. If right, then and right and add val to string. Now, if we don't have a left,
We need to have else condition. Since we don't have left, we just need to append the null or whatever our
add
um,
this.
preferred character. Yeah,
Okay.
yes.
And same here. Else add this dot to string. All right. And now we also need to add our delimiter. So it's going to be this, and also the value. It's going to be value plus this, comma. And then at the end, we return the string. Looks all right. So
Yes, but we need to avoid
avoid.
to have a trailing comma or yeah, we need to
It
avoid to
wouldn't
have a
really
trailing
matter. It wouldn't
delimiter.
matter since the splitter removes them.
Uh-huh. Yes. All right.
So, and even if
Yeah.
we have an extra
Yeah. Yeah.
element at the end that is
Yeah.
empty,
Yeah. Yeah.
we can
Yeah, all
remove
right.
it
All
from
right.
here. Okay.
Yeah. Yeah. All right.
So
Doesn't matter.
we make, so we have a q equals dq, and then let's make the root, or let's add this root, which basically can just be like this, right? And now while the q, we pop q, which is node equals pop left. So if node dot left then q dot append node dot left, and we need to have a string here that we're adding onto. So s plus equal, and in this case we need to transform the element into a string, so it's gonna be node dot val, I believe that's what they call it. Yes, val, and plus a comma, and we're gonna do the same. Oh wait, string. So s plus equal dot comma.
I think there may be an edge case here also, because what if the node was last node? Should we add a comma?
It is pretty safe in this serialization. The split removes the comma, and we can remove the last element of that, or it just wouldn't matter because we're guarding against it here and here. I feel like
Yes,
it wouldn't really
doesn't matter.
matter,
Yeah,
but we can
yeah.
remove it from here somewhere. It's
Okay,
just gonna
okay.
be an empty element, just a empty string. All right, so we can just copy this right here, and if right, then node right, node dot right dot val. Right, that's well. So either we can remove this from here and have it outside, or we can initialize the string with the first element. But I feel like just removing this and putting it here and adding the current value rather than the children's value. And in here we can just append, knowing that we already have this in the string. So right, and then we return s. Let's print s first. And let's just comment this out just to see if the code works or not, since this is gonna give us an error. Okay, errors, of course. While q left, let's run it again. Q dot left. Tape has no. Okay, so we check if the node is empty or not, but I'm not sure why. Oh, if the root is empty, if there is no root, we can possibly add something here to check. If not root, then just return empty string. Okay, so it is not like we expected. So it should be 1, 2. Okay, no, it is not how it should be. So it's adding the nulls before adding. Look at this. I feel like this doesn't correlate with what we have here. So we're adding for the name for the children, but here we're adding for the one itself. So let's do if node, or let's do it here. If node, and then else it's gonna append. So basically it's gonna do this. So these shouldn't matter. Yeah, I feel like this is what's gonna make the in-order traversal. And then we just don't care for these since it is node. Okay, let's try that. You can just put them inside here. Since if it is not node, then it won't have a node left or right. Let's see. Okay, now it works. So now we have a 1, 2, 3, and then the 2 nulls for 2, and then 2 elements for 3, and then the 4 nulls for 4 and 5. All right. Okay, now that we know this works, and let's now replace the something we left in case 2, since it is going to be print in it. Oh, since it is going to be an empty string. So let's go here, replace this with this. Let's see if this works. No. So invalid literal. Okay, we can remove then the last elements, with which I'm assuming is the issue here. Can just do like this -1. Okay, that is great. Let's submit it. Let's remove any prints. Yeah. And let us submit. Okay, pop for an empty queue.
Oops.
So
Hold on. Yeah, we need to check.
so deserialize. So in here we need to check. So maybe if, oh, let's keep it if Q, if not Q, then just break.
Uh,
Let's use this. Let's run it. No. Okay. That's an issue. So the queue is empty, but we still have 2 elements left.
Why not try checking just before you
Hmm?
try checking just before you pop?
Just before? What? Just
The moment
before
when
you
you pop,
pop. Okay.
yeah.
Let's see first this one. So the queue is empty. It had 5 and we're at 6. So it did, so it had 5 and it added 5, but it did not add the children. What kind of tree is this? So it's
That's
1, 2, 3, and then empty, empty, and then 4, 5. Let's make a tree of this to see it. So it's gonna be so 1, 2, and this is gonna be null, null. 1, 2, 3, and then it's gonna have 4 and 5, and I believe 4 is the one that has 6 and 7, since we don't care about nulls here. Let's have 2 is 3 is 4, 5, and then 6, and then 7. All right. So once it got to 5, it doesn't have anything, but 4 should have added. So where's 4? Okay, so here's 4. 4 should have added 6 and 7, which it did not. Oh, it's because maybe they're out of bounds. Yeah, it's definitely because they're out of bounds. So 4 is 0, 1, 2, 3, 4, 5. And yeah, it's gonna be way outside. So I don't think our little formula works with the last elements. Any new ideas?
Can you print the string? Can you print the constructed string before the
Okay.
deserialization starts?
Alright, so here, right? So print us.
Can you make the code a little bit more verbose, like it's just full screen, if you can, please?
Let's see. Okay. But I can copy it in the comments if you want. But I'm not sure how bigger I
No
can
worries.
make it.
I think last time you were able to
Well,
move this test pane
I
to the left
believe it
hand
was
side.
just this, but I won't have access to the.
No, yeah, I told you you were able to move the testing pane to the left hand
Oh,
side, so you
right,
can
right,
access it
right.
easily.
You're absolutely right. Let's see. So I did this.
Exactly, yes.
Yeah. Okay. And
And hit
then
F11.
oh,
I don't know.
this.
F11, yeah.
Okay. Better.
Yep,
Okay.
absolutely.
So basically, this is our string. So 1, 2, 3, and then 4, which is 0, 1, 2, 3, 4, and then this is 5, 6, 7, 8, 9, 10. So it's empty. But here are the children. This is what they have, so this is correct.
So maybe maybe the last two children, they're they are not the children maybe of the node 5 or 4.
They are. I believe they are, because 1 has 2 and 3. And then the children of 2 are these.
These null.
And then 4. And then the children of 4 is 5. No.
The
Oh, let's go
children
back.
of
Let's go back.
nah, yeah,
So we
go
have
back to the
1
one.
and 2 and 3. And then null
One,
and null and.
two,
Oh.
null on null
Null and
for 2.
4 and 5. And then 6 and 7 and then nothing. So it is correct. But for some
4
reason,
four
4
for 6 and
4's formula doesn't give us 6 and 7. It gives us dots. This is why I assumed at first this formula is not for the level index process. Even though it works
Yeah,
for the
I
previous
think I
ones.
think
I'm
I
not sure
think
why.
Loay was right when he
About?
said that the next children, the left and right children will be the next two nodes for the campus. Maybe.
Right. So how are we going to do that? So the left, so the current is going to be, for example, 2, and then 3 and dot are not the children of 2. Or do we skip these? Perhaps not.
Okay, you remember last time, or actually last time I was here, when this problem of the hills and the lakes, you remember
Are
it?
we going to take a break?
When you went through, when you drew,
Oh,
no, no, no,
okay.
not like the other one, but that was the one that you like. When you
Ridiculous.
drew the
Pretty
problem
hard.
from the beginning, step by step, it helped us catch the patterns even better. So
So
try
we
to try
know,
to try to
we
write
know. Okay.
draw this
So I like the idea
try to
of
draw
the, yes, yes, we will draw it. So this is basically our
I'm
tree.
sorry, like make the list not draw it.
Let's
Drawn
what?
already. I mean
Oh, okay.
the list itself. Like write the list one by one to see to catch that the number of like the space between the children, the father and the children when created. What happens for the left and the right? What happens when if you're on a different level?
So at one,
So
the children are, um, at one, which is the index 0, the children are 2 with an index of 1, and 3, which is an index of 2, right? And then 2, which is an index of 1, gives us children of dot with an index of
um,
0, 1, 2, 3.
I think I have an idea of how
Go on,
to solve this,
go on.
but I think we can use two pointers. Like one goes faster than the other, like the tortoise and her approach. If we start at the first index with the root, we add the next two children using the faster pointer. Then the the slower pointer goes to the next node, and the faster pointer goes to maybe the next two nodes goes
And
to
we
add
ah,
we know that this is gonna work for this.
what?
It seems so far that it would work, but let's complete this and see if we see the pattern. If yes, then
Okay,
that
okay,
is a good idea.
okay.
So 3 of this is gonna go to 4 and 5. So 4 with an index of 5, and then 5 with an index of 6. And I don't think it's gonna work because, so if one goes faster, 0 is gonna be 1. When it goes to 1, it's gonna be 4, but shouldn't this be like 8 or something for it to work? And we're also skipping from 3 of an
sure.
index of 2 to 4 with an index of 5. So it's not consistent.
Sure. Try to you see this light this list you're pointing at?
Yes,
Try to make it again.
that is not ours. That is the one they gave us. And
Yeah,
ours,
it's the one for the tree that you've just drew.
yeah, and this is the one that we got, which is the same basically. So you want to make it
Yeah.
again into a tree?
Yeah, like, no. I mean, the tree is there. Try to make the list itself like the queue that we have.
So
Like just write 1, 2, 3, null, null again.
again.
There's something I want to make note of. I tried to make with my whiteboard, but I was confused by looking at the whiteboard and then hearing you speaking. So we've got 1.
1,
We're gonna add it, and add afterwards. We add 2
2, and 3.
and 3. That's the last thing that we added. But the place that we're like reversing or like the index, the current index, or the cursor, so to speak, is at 2. So 2 will add dot and dot. Holy moly!
Okay, doesn't it sound
Okay.
like we're skipping these two? So perhaps when add in like, even though we're skipping this, we add like, okay, say we for example loop through the queue and we have an index, and the index goes at each iteration, but once it has like a, like something like this, it just skips it. It adds like one, it increments once, because like to accommodate, for example, this.
Two is for dun, 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 dun. And four like
Seven,
four is like
and then seven, eight,
aim that.
five is empty.
Okay. Oh god. Like those are just jumping and overriding each other. If I see correctly, I'm not really sure. But if we are at four, we're not adding six and seven because
We are
if we
adding
try to
sections.
access it, it's what? What did you say?
Okay, yeah, we're not adding six and seven since their children are null, but we are making
Maybe
them.
maybe not because of this, but because we reached the end of the list, the cursor reached the end, like a bunch of
Well,
nulls, and then the
okay, okay,
end.
okay. So our list, the
So
one
maybe this is the
that
problem.
our string returned is this. This is the one that they have. This is what ours returned, which has a bunch of dots at the end. So it's not maybe a problem of reaching the end of the list.
It's
But the previous issue was that the formula that we were using, when it came to four, it gave us a, like, it pointed us to one of these, not the ones right close to it.
so we keep moving, and then we then add the last level. Hang on, does LeetCode have a debugger?
I believe you can pay for one. Yeah.
You can pay for it. Okay, good.
Maybe.
VS Code is our friend here. We don't have to pay for it, right?
Who?
VS Code. We can copy the code, uh copy the code, put it there, and we have Python installed. I believe you must have having Python. So we use the debugger of VS Code to go us
Debugger of
block
LeetCode
by
is a
block.
premium option, my dear. Premium.
Um, VS Code.
VS Code. Oh, okay. I can I admit that I've never used the
We
debugger.
don't have to pay for it.
Okay.
Well, the last time I took it when I was taking CS50, thanks to Professor David Milan, later on I didn't try, so I admit the same here. So anybody, I think, yeah, hang on. I think you just set breakpoints. Okay, this red dot, and then you run the debugger, and you will see a window
Okay.
at the left giving you all of the
What do
variables, the
these, okay,
values of each
what
variable.
do they do? What do they do?
When you set breakpoints, when you run the debugger, the code stops there, and then you have some bunch of arrows left and right and stop, so you can tell it, okay, skip one line or skip one block or move to the next breakpoint. You choose it, either line by line, or you move like you have a breakpoint before you return. You have a breakpoint before actually you maybe compare the left and the right, or like the right and the left to actually check it, or you got what I'm saying? So you can like without you trying to imagine, okay, when we are here the values are here. No, it's just in front of you, the values in front of you, so you analyze, not just try to imagine. It just leaves some burden. You got it.
I think that the learning curve will take us like some time.
As you wish.
I mean,
Hopefully.
if somebody knows how to do that, like, for sure, then maybe they can share their screen and we can debug there.
Okay,
But I feel like it will
count
take
two
us
minutes,
more
open
time to
VS
do
Code, and
that.
if we're stuck, leave. Because I believe I know. Guys, anyone here used it or any like debuggers in the terminal or something? Okay, I think I know. I think I know. Just open VS Code and 2 minutes. We're stuck in it. Let's leave it to save some time. You want to save some time eventually, right?
Well, let me connect.
Guys, so you the ones that were a little bit silent. Have you noticed any patterns you can help us? Like, I believe
I feel like we
I
need
myself.
to perhaps.
I feel
Okay, go on, please.
I feel like the problem with the pattern is because of the dots.
Should we replace them?
If we skip the dots, we can see the pattern working. Like,
Yes.
let's look at the string 1, 2, 3, dot dot 4. If we started at the zeros index with the number element 1, the next two nodes are the element at index 1 and 2, right? Because they are not dots. Then we move the slow pointer. I want to think in terms of the approach I said earlier. I don't know if it works or not. I just want to try it. So
Guys,
Oh, nice.
the slow pointer the slow pointer would be at index 1, and the faster pointer would be at the two dots. This means the two dots should be skipped because the node is already created. Then the slow pointer goes to the 3, and the fast pointer would be at 4 and 5. So 3 should add the 4 and 5, and the fast pointer would be at 6, 7, and I don't know if you
I think
with me or not.
I understood, and I
Justin, are
agree.
you saying that? Are you trying to eventually achieve a goal that you're traversing? It's like you're tracking, you're separating the nodes or the queue of the nodes that you are accessing with the list of output that you're getting, or like a list of I mean the characters, the list of characters representing the numbers. Are you saying so? You separate. It's like you're having a queue that you're traversing and with no nulls, just a queue. It's a queue, a bunch of nodes listed, and
Yes.
elsewhere you're storing the children. Is that what you're trying to think of trying to go to?
I actually didn't get your question.
You're saying you'll be tracking. I mean, are you trying to have like a place where you're traversing one after the other the nodes, and you're storing somewhere else the actual like
Yes.
the values inside the nodes, including the nulls which doesn't exist, so you can like separate the traversing with the output that you have.
Mm, I don't know how to implement it really. I just have this idea and I wanted to
Can
explain.
I
I don't know. I don't know if it really works or not.
point out one thing? So basically, if we go with the double pointer idea, one pointer is gonna point to our nodes, and the other pointer is gonna point to their children. If you notice here, they are in order: 1, 2, 3, 4, 5, 6, 7, 8 in the indexes, right? Our first pointer can just be our queue, right? That we add to it. We don't necessarily increment it since it's just elements in the queue. And then our second pointer can just go through the list normally and just increment as it goes. So once we pop the queue and we have a 1, and we just increment once, we have 2, we increment twice, we have basically 3, and then we pop again, and these obviously are added. We pop again, which is 2, we go to 3, and we don't have anything, and we increment regardless, we have 0, again, a null, and then it's nothing, and we increment regardless. So we're still at 5, and the 3 that was added here goes back when it's popped, and then we add these two as we go. So the second pointer can point to the values or children, if whether they're like valid or just dots, and the first pointer can be our queue. Does it make sense?
Yeah.
So basically we would have something similar to this, but we're looping, or I guess while queue, and then we pop left queue, and we check if, for example, we perhaps would have like an index equals 0, and then we increment by 1 or something. But since we're starting with this and we already have 1, we can, for example, start with 1, and then we check if nodes index equals, or doesn't equal in this case, a dot, and if it doesn't, then we make the node and attach it to the root, which is we've popped here, and we're just incrementing regardless of whether or not it is a dot. So index plus equal 1, that means that we're skipping it if it is a dot, and if it's not, then we make the node, and perhaps we do the same things here. If nodes, now that it is index plus 1, it's going to be index. If it doesn't equal a dot, and then again we make the node, and here like attach it to left of root, and here make the node again and attach it to right of node, and again we just increment no matter what. Does it make sense? I feel like this should work because the queue holds these elements that we, oh yeah, and obviously not only we attach it, but we add it to queue. And same thing here, we add to queue. So the pointer, the first pointer could be this. This is like the slower one, but instead of actually being a pointer, it is just elements in the queue. And the right one that is in order, right? 1, 2, 3, 4, 5, 6, 7, 8. It just goes through each of them and increments no matter what. What do you think?
Let's try.
Okay, can try it. So this, I believe, either like we add the indexes first and we remove this, like we start it from 0, or I believe we could just initialize the queue with the root and make the root here. So make the root and add to queue. So it is initialized, so we can just start from 1. And at the end, we just return the root that we made here. So let's try with this. So yeah, it's basically the same thing we did here, except and then so we already made the root, we already made the queue, and we're starting the index from 1, and so node equals queue dot pop left, and if node's index doesn't equal a dot, then we make the node, which is, for example, left equal out with the value of node index, and we attach it to the left of root. So we have not root but node dot left equal left, and then we add it to the queue. So queue dot append left, and we increment the index, and the same thing here. If node index, guess we just copy this. Right. Okay. And we return root. Does it sound okay? Let's run it. Okay. That passed even the test case that I had an issue with. Let's submit. Okay. All right. 59, not bad. Not bad. So this is the
Nice.
solution with BFS. I'm not sure if you guys want to explore DFS or not. It's been like 2 hours or like a quarter to 2 hours. The DFS solution is pretty easy, to be honest. Less like mental hoops and stuff. You wanna go there or just
I
take
wa-
the rest for the day?
DFS, I think, depends on which traversal or recursive traversal that you want to go with.
Okay, DFS
Pre,
will be I
pre or
believe pre-order, yes.
pre or in or
And with the recursion is gonna be pretty
yeah.
easy. You just give it each root, and the root runs the or launches the DFS on its children, and the children of the children keeps going. Do we want to do it really quick?
I don't mind, but I just want to optimize this solution.
Okay,
Uh,
how okay, so we can either go DFS or optimize this. And if we want to optimize this, then we can do that. How do you think we should do that?
I think that when we reach the half index of the length of the list, we should stop like I don't know
What do you
if
mean the half
this is true.
index of the string? Why?
Um, I'm not sure, but
Oh, you mean as in like here?
I mean like when we added the last seven, should we really go and search for the
So you
for
mean that so
traverse
this
all
is
the
in
nodes?
serialization
Yeah,
or in deserialization?
in the deserialization.
So the deserialization, I don't believe it even goes here because once 7 is explored, then the queue is empty. 7 doesn't add anything to the queue.
Uh, okay.
Print
Um, I
just
was thinking about
indexes
something else.
and check
Are we
which.
done with this solution for now?
Excuse me.
Uh,
Okay,
things
just continue.
So 0, 1, 0.
if we can have C like buffer in Python, so instead of making join, which is all of in time
The
complexity,
index is the index of the strings, not the queue. I mean, the string with the dots.
Yeah.
So, yeah.
So we're just checking which index it stops at. So in this case, 17. I'm not sure. 0, 1. Oh, well, not 7, 13, but this is the one. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it does get to here, which is interesting. Oh, now I see what you mean. Yeah. I'm not sure then how we're checking the nodes. But I guess, I mean, logically the last node it's C and it's 7, so it really is not going past that. I mean, I guess we could perhaps possibly optimize it in serialization so it doesn't go
No,
all
no.
this extra.
I think I think it's
Otherwise,
optimized.
okay.
I think it reached here because we printed the index. The index is what will tell us if we reach the end. Like we are incremented the index, right?
Yeah.
So the index will go through the dots without doing anything until it reaches the end of the list. In this case, we reach the element before the end of the dot
And
before
it's
the
still,
last because we printed the index at the beginning of the while loop. If we printed the index at the end of the while loop, because we increment twice in each loop, we will reach the last
yeah,
dot,
we will
right?
reach the end, and our queue will only be until like 7. And it will stop
Yeah,
here, and the children of the 7 is possibly here.
yeah.
Okay. So, do we stop here? Do we keep going?
I don't mind
Okay,
to
I would
see
say
steps first solution.
I
Yes,
would say
what?
that if since we're done with this solution already, and we've been just jumping error and trial until we've reached the successful solution. So I believe we need to go through it one more time to actually see what works, like systematically, just one by one. We see actually what worked because we changed many things down the road or down the way, if that's the right way to say it.
It changed
So
everything.
I don't think that except for you who worked on the solution, even you yourself could be confused exactly what exactly worked and how we solved it. So if we go through it once, that would be really more useful.
Does anybody wants to take the mic and go through it? If not, I can do that. But if somebody feels like they need to go through it one more time to cement everything, they can take the mic and explain it.
Does that depend on how much you understand the solution?
Oh, no.
Go for it,
I
guys.
Well, I can go.
okay, yeah, that'd be great. Go on.
Okay, so to the top. And again, you said it doesn't depend on how I understand the solution, so I don't want to stutter much. Just wait your. But okay, so class gotta forget about this one. Okay, serialization. We're just okay, encode a tree into a single string. Okay, if not the root, if
Right?
not
Can
root like
you
the root,
just
we have
please
no indexes. We return nothing. Again,
tone it
some of these
down,
things.
a little bit.
What?
You are speaking too fast, and
Okay, thank you.
we are not following up. Like for me, I cannot follow up. So make it slowly and
Thank you. Okay, so if we do not have a root, basically no tree, so a string, we will return an empty string. We don't have nothing. We do not have anything to actually say. Queue, we're creating a queue. Queue is just consistent for now. Only have the root, one node, and this S, the result that we will be returning. We didn't traverse anything, so it's just an empty string for now. While queue, which means that while we still have something in the queue, correct?
So, well, there are more elements to explore.
Yes. node is the well node the current node that we have is the left the like the queue to top left. So it's the first thing that we added, or the first thing that we like in the queue that we haven't really explored yet. The left one, if the node is there, we add its value, if I believe correctly, s plus equal string nodes dot value plus this node. I think okay, leave it for now. So didn't you think that we can just make a list of the values with a negative if it has a negative? So we just make a list of them, and then later on, to solve the problem of exploring like negative or positive, and then we use the join at the end of the function, or this won't help.
Absolutely do that.
Oh, I
Yes.
think it will lead to the same solution. We
Can
need
have
to explore it at the
let's append um node.val, and here we would just dot append dot and then s or dot join s, right? And then
yes.
we could just remove this, turn it.
It just looks prettier, but it turns out that I misunderstood it. It doesn't work. Okay.
Oh, oh, so
We can get it back as the way it is
that's
for now.
oh, very good.
Okay.
Intro.
What's the problem?
Oh,
It was working.
it is gonna work again. I promise. Okay, go
Okay.
on.
Right, it just looks prettier, but that wasn't what I think about. I was thinking, that thing, like this list thing.
What, it is a
Okay,
list
we will see
now.
how we solve the negative. Yeah, yeah, no, I was confused about how we solve the negative when we have a negative number in the deserialization, but we are here at the serialization, so it won't make much difference if I'm not mistaken. So, okay, if we have a node, we will append its value, string node.val, we will append its value, and then we will append to the queue as well. The left and the right basic three traversals, what and then we append the right node. Else, if we don't have any nodes, we will append the dot, which that's what we replace, what we are replacing the non-existent nodes, and then we will return the list. That's pretty easy, I believe, like basic DFS. Deserialization. Here's the spicy stuff. So, am I slow enough? Indeed, I sometimes speak really fast.
That's good.
All good, guys? Okay. Deserialization, we have a string, we're receiving a string, and then we need to make a tree out of it. Decode your encoded data to tree. So we are getting a string, and then we need to get to return a pointer to the node, to the root node, I believe. I'm sorry. If the data is not, is just like empty string, so we don't have a tree, so we just return none. Nodes equals data dot split. Okay, so we're splitting. Oh, okay, good. So we're just making a. Okay. So I think here we're making a list of just small characters representing either a number or like a number preceded with a negative. So we already solved it when we have a negative number, and then the root. Excuse me. The root is as tree node. Okay. Don't you think that we can make it a bit easier that starting from now before we continue we make like we map a function to like an end function to to like turn the all the data into like a list of numbers instead of we you know make the code busy with changing from a string to an integer
I
or
don't
not.
think I understand. What? Can you repeat, please?
Okay, the data here is still string, right?
Yes.
Hang on, these nodes the tree have get back. I'm sorry. Like go to the top. Are the nodes strings have string
So
values or integer
the
values?
node has self value, which I believe is an int. and then
Okay.
it has a left and a right. But the
So
value I
okay,
believe
so
is an int. Or I don't think it matters because again I forgot to put it
uh-huh.
into an int and they didn't even complain. So
Yes. Oh yes.
I guess we could
Yes, right
again
here.
just
Okay.
remove
So
this and it wouldn't matter.
uh-huh. Got it. Thank you. Okay, so we have to so now we just nodes. Okay, we have just a list of the nodes that we have. Okay. Good. Yeah, yeah, correct. Correct. So node equals data dot split split them based on the or make the separator is a comma. So I have like a list of instead of with just one string, we have a list of the values so we can traverse it easier. Root is three what? Okay, three nodes.
We
What is
made
two?
this,
Okay,
so
okay.
this is a
Oh,
node,
okay, yeah.
an instance
Yeah,
of a
I
node.
making a root, making like a root node because it's gonna be the first one, the first thing we add to the queue. As well, we would make do the same. So the key. Okay, so that's what I'm talking about. IDX is one. Starting from index one, we are neglecting the first root, the first node because it doesn't apply. The rules of the formula doesn't really apply to it, if I'm not mistaken, because the
We've
children are
already gone
following it
through it.
directly. Huh?
Because we've already gone through it. We already made the node for it and we added it to the queue. So
Oh,
you're skipping it.
okay, good note. I didn't take note of it. Ah, yeah, got it. So node is so while we have something in the queue. Can you bring the image of the tree? It could be helpful visualizing it. No, I mean, doesn't it show up in LeetCode?
The tree in
I mean,
LeetCode,
I want to.
I don't think
Yeah,
LeetCode.
if you scroll up or down. Okay, can
I
you if
believe
you
it's
can
this
bring it?
one.
Yeah, this is the one. Yeah, I think that would be easier for us to follow up with the code. So we're adding the root, the first one in the string, which is one in this case, and then okay, node, while we have something in the node, okay, we remove the first thing that we have, which is going to be the root here, and then if nodes index if nodes the index we are in, which is going to be one here, it's not a dot, so we make a note for it. We make a note for it. So the left is make a note for it with this character that we have, and then we append it to the existing node. So node.left equals left, and then we append that one to the end to see later on when it comes to when it's like rule comes, not rule, like when it's position the queue comes,
Yeah,
we can see how what if it has children or not.
correct.
Index, now we increment the index to move on, right? So we can capture the right. If nodes the same way, if nodes index, if like the index that we are at right now pointing at in the string is not dot, so it actually represents a node, right? Equals tree node. We're just making a node, a new node, and then adding it to the existing node that we have. Node.right equals right, and then we append this one. We append that. Okay, did I get lost?
No, no,
Queued
you're going
append,
great.
right? So yeah, the node that got it. So we append it to the one that we have. No, we don't append it to the one. Okay, so that's the children. That's the right child.
Yes, that's the
We're
left
adding
child,
it.
and this is the right child. We create
Yeah,
it,
yeah,
link it with the root, and add it to the queue to revisit it.
got it.
I think you should bring the string with the dots
Oh,
to look at the
okay.
solution. It will make the solution easier. Yeah.
Not sure where I put that. I'll just put that here. Okay.
Yeah, that's it. Okay, I think yeah. So we with the end of this week, we ended this for loop because there's nothing else. We pooped everything out of the queue. We just returned the tree that we have. So back to square one with the pseudocode to the tree. One last iteration of the algorithm. So you think it works? But Sabah, do it. You do it. You started with it. If you may re-go through it. Just forget about the code now that we wrote. We now
The
I think we
second
have
time?
like an understanding.
Do you want me to go
No,
through the
just like
code for a
this.
second time?
Okay, no, not no, no, not the code. I mean, this just the idea. Like if we
Okay.
made a because you have the cursor, so you can like point at the tree and point at the string to like visualize it again. I'm not no code, no code, no code. Don't worry, not even a pseudocode.
Laser.
Yeah, yeah,
Okay.
exactly. Because you have the
So
pointer.
so basically we serialize, aka we make a string out of this tree. We start with the root of the tree. We add that to our queue, right? And then now that
Good.
we are at, we pop the first element of the queue, which is 1, it explores its children. If this child is not null, it adds it to the queue. If this child is not null, it adds that is at the queue, and also it adds this to our string, right? Now that we pop this, we move on to the next element, which is 2 that was added first. 2, again, it's explored. This is null, this is null, so it doesn't add anything to the queue, but it adds this element to the string. Moves on to this, it pops this, explores the children. 4 is not null, it is added to the queue. 5 is not null, added to the queue, and then we add this to our string and we keep going. If we don't have anything, if for example, but our node is null, aka for example this is empty, then we just add a point. If not, then it gets basically explored. So that is for the serialization. For the deserialization, which is, let's put this back here, make it bigger. And so let's get back our laser. So basically we do the same thing we did in BFS. We start with our first node, and then we have our queue that holds the elements that are valid, the nodes that are validly, like that should be explored. And then we have another pointer that just goes through the length of the string. So 1, for example, its kids are 2 and 3. And the int or our index is going to be at 2, is going to be at 3. So we add 2 as a left, we add 3 as a right, we add them to our queue to be explored. So once I get to now 2, 2, this is its index, and or the index of its children, right? So it's the index after 3. So this and then this, and nothing gets added to the queue. And then since the queue now only has 3, we pop 3, and the next indexes are of these two elements. So this is a left and this is a right, and both get added to the queue. Now we have 4. 4 gets the next elements or the next index after 5, which is 6. This is a left, this is a right, and the index is at here, and these two are added. 5 is empty on the left and on the right. 6 is empty on the left and on the right. 7 is empty at the left and on the right. And now we have nothing in our queue. It removes the queue, and or it leaves the while loop that checks if the queue is full, and then it returns our route that we made outside of the queue. Is it clear?
Uh, yeah, I think that's clear. We did what we have to do.
Yay, great.
Thank you so much for this one.
All right, perfect. So, I guess I could add this into like the comments. So, or just this one. If somebody wants to attempt to, um, I guess make a
And by the way,
better
if we're
version.
doing this every single time, then why not making like adding it on a thread to each recording, or like on a thread to each recording, or even make a channel for it, like just
I,
yeah, just a thread to each recording.
you know what? I might start doing that actually.
It's
Maybe
kind of
just,
easier because the
yeah,
comments just
attach
get lost.
this to, attach the code to each record, and that is a nice idea. I will
Thank you.
I will let Monsif know. He's the one who actually posts the recording. So yeah,
All right, all right. I hope
great.
send
Thank
my
you,
greetings
everyone.
to Monsif.
Yeah. All right. Thank you, everyone. That was a really nice session, very interactive. And
You are welcome, and thank you for your efforts and time as well, of course. And good night, everybody.
everyone, Until the next session. Bye bye.
Bye bye.